Differential equations are equations that involve variables, both the independent and the dependent variables, as well as derivatives of the variable. And when we want to solve a differential equation, we want to find the equation such that when you took the appropriate derivatives and plugged those expressions in where the derivative notation is, and the expression for the function where the function notation is, and you simplified both the left and the right side, you would get a true statement. Now when we're solving differential equations, we first get what's called a general solution. And then if I don't have any other information about the function, like an ordered pair point that it goes through, then the general solution is as far as we can give. But then if I have an ordered pair or information about the input value and then what the output would be, I can use that to find my constant terms value and then write what's called the particular solution. I've done a couple different examples of this in another video that I'll link to the description of this video. For now, we're going to look at additional examples when we're solving these very, very introductory differential equations. Now, on the work with solving differential equations, we need to remember our integration techniques and our integral rules. And so I've written up the very basic indefinite integral rules here. When we need them, we can refer to them over on this side. And then I've also written up the properties that the integral of a constant times a function with respect to x is the constant times the integral of the function with respect to x. So that's saying you can pull number factors out in front of the integral. And then we also have the integral of f of x plus g of x dx is equal to the integral of f of x dx plus or minus the integral of g of x dx. So I can integrate term by term. Now notice, I do not have a property over here that says anything about the integral of f of x times g of x dx. And in fact, we won't get one. There isn't an integral rule for the product of two functions in general. I also don't have one for the integral of f of x divided by g of x dx. We don't have it here, nor will we get one. So the main thing you need to realize is that sometimes we need to rewrite these integrands if they do involve some sort of a product or a quotient so that it conforms back to something that we can integrate. Sometimes when we're looking at them, we might have a function who as its derivative was a product of two things. So when I identify that particular thing having been as a derivative of a function, I go directly back to it. But I don't have a general rule for integrating the multiplication of two functions or dividing two functions. So with that in mind, let's come over and look at this example. So here it says the second derivative of y is equal to -6. And then I also have this extra information that the first derivative of y evaluated at -1 comes out 3, and the function itself evaluated at -1 comes out 4. So I'll use this information about our original differential equation to get our general solution, but then I'll use this extra information to find our particular solution. Now if the second derivative of y is equal to -6, well remember the second derivative is the derivative of the first derivative. So if I'm going backwards, anti-differentiating, then my first derivative is going to be the indefinite integral of my -6 and then dx. Now integrating -6 dx, I have y prime is equal to, well that's thinking of this as -6 times 1. So you can factor out the -6 factor times the integral of 1 dx. And the integral of 1 dx is x plus c. So I have this y prime is equal to -6x and then plus c. Now I don't need to take that as a parentheses and multiply -6 times c here because c is a constant term. and it'll be the value it needs to be when we plug in our extra information. So that way I always will just put that plus c term at the end. Now, before I go on to the next phase of things, I need to find out what the constant is for this particular setup, and it's the derivative that we're at, so we need to get the specific information from the derivative. Now this y prime of negative 1 equals 3, that means if you put negative 1 in for all the x's in the derivative, then the value you get out for the derivative is 3. So 3 is on the y prime side, and I'm going to put a negative 1 in for the x on the right side. And this allows me to find my constant term. So then this is 3 is equal to, well, negative 6 times negative 1 is positive 6, and then plus c. Subtract your 6 from both sides, and we get c is equal to negative 3. That means right now our y prime is equal to negative 6x minus 3. That's just gotten me to the derivative though. I haven't gone all the way yet to find the actual function itself. I need to do this process one more time and integrate it again. So my y is equal to the integral of negative 6x minus 3 dx. So y is equal to, well, term by term, and then think about that constant factor coming out. So this is a number times x to the positive 1 power. Letter base to number power as long as my number power is not negative 1. To do that, you add 1 to the exponent and divide by that. So I have my x. It's now to the first power. 1 plus 1 is 2. And when I take negative 6 and divide by 2, I get negative 3. And then minus the integral of 3 dx is 3x, and then plus c. This gives me my general solution to that differential equation. It is a function whose second derivative is negative 6. But I also want to make sure that if I have these extra conditions given to me, that I find the correct value of my constant term so that these conditions are met. So right now we have the general solution. Of y is equal to negative 3x squared minus 3x plus c. And to find the particular solution, I have that y of negative 1 is 4. So putting negative 1 in for the x's gives me an output of 4. So I have 4 is equal to negative 3 times negative 1 squared minus 3 times negative 1 plus c. Now remember your order of operations. Negative 1 squared is 1. 1 times negative 3 is negative 3. Then negative 3 times negative 1 is positive 3, and then plus c. Well, here when I collect like terms on the right-hand side, negative 3 plus 3 is just 0. So negative 3 plus c gives me c. So 4 is equal to c. That doesn't always happen. It was just a specific case here where it did. So now my particular solution is my y is equal to negative 3x squared minus 3x plus 4. So here is my equation that satisfies that differential equation. It's the solution to that differential equation, where if you took the second derivative of this, you would get negative 6. So negative 6 would equal negative 6. And also, if you put negative 1 through for the x's in the original equation, you would get 4 out. And if you put negative 1 through the derivative, you would get 3 out. So it meets all the conditions of the original differential equation. So you can check your solutions of your differential equation by taking the appropriate derivatives, seeing that it makes it true, and then also making sure that running the values through, if they give you those, you get the right values out. So next up, we're going to look at an application of a specific type of the solution of a differential equation. So here our question is, a ball is thrown with an initial velocity of 60 feet per second from a height of 6 feet. Find the position function of the ball, giving the height s as a function of time t. So when you think about throwing the ball and the path of the ball, the release of it was 6 feet above the ground, and your velocity is 60 feet per second. Now, there's a couple things that we need to realize here. If you're throwing a ball and it doesn't have any other action on it after the release of the throw, the action is actually just that acceleration due to gravity. And you have to look at the units that are used in the setup of the problem to know where to start with your acceleration due to gravity. So if your measurements like this one are in feet and in seconds, your acceleration due to gravity is negative 32 feet per second per second. So that's our acceleration function. It's a constant, and it's negative 32 feet per second. Now, if you're looking at something being measured in meters, where the time is in seconds, then it's going to be a negative 9 meters per second. So always pay attention to that for things that are on the Earth's surface. If you're looking at possibly like on the moon's surface, then you would have to get the acceleration due to gravity on the moon, because the mass of the moon is different than the mass of the Earth, so the acceleration is going to be a different force. So this is what we have for our acceleration function. And then we also have the initial velocity is 60 feet per second. Now, velocity is our function v of t, and it's the initial velocity. It's at the very start when time is 0. So that gives me, for the velocity function, that if I put 0 in for time, I will have a 60 feet per second that comes out. And notice, for acceleration, that's for all time of it. But for the velocity, that's changing over time. So we're just saying the velocity specifically at the initial condition, time equals 0. And then it also says, and from a height of 6 feet. Well, if I'm looking at this height as s as a function of time t, then 6 feet is my initial position of the ball. So s of 0 is equal to 6 feet. And that's just gathering the information out of the problem. Now, we want to recall what we did when we did derivatives, and we were looking at our projectile motion type questions. So remember, if we started with the position function and we wanted the instantaneous velocity function, the position function's derivative was the instantaneous velocities function. And then if I had the instantaneous velocity function and I'm looking at instantaneous change of velocity with respect to time, that's your acceleration function. Now, going backwards on it, we're starting at the acceleration function and we want to get a process to take us back up to the position function. So position function's derivative is instantaneous velocity. The instantaneous velocity's derivative is our instantaneous acceleration. So if we're starting with instantaneous acceleration, we have to integrate to get to the instantaneous velocity. We're going to get a constant term there in the integration process, and because we have specific information, we'll be able to find that constant value. And then the integration of the instantaneous velocity function gets us back to the position function. And again, we have some initial conditions that we'll be able to find that constant term. So our first step, we're in the acceleration function, is to integrate to get to the velocity function. So the velocity function v of t is equal to the integral of a of t dt, but that's just the constant negative 32 dt. And I know to do dt because it says I'm looking at a function of time t, so that's my independent variable. Now remember, when I'm looking at integrating the constant with respect to t, that's going to be negative 32t plus c. And then at this point, a lot of times we want to say c sub 1 because I know I'm going to do two phases of this. So I'll have a constant term at this phase and then another constant term at the second phase. But we want to find that constant before we move on. In the velocity, if I put in 0 for t's, I'll get an output value of 60. So my output value is 60 when my input t value is 0. Negative 32 times 0 is 0. 0 plus c1 is c1. So c1 is equal to 60. That gives me my instantaneous velocity function, v of t, is equal to negative 32t plus 60. Now I want to get to the position function though. So I want to get to s of t. So we were at the acceleration function. We integrated to get to the instantaneous velocity function, found its value of its constant term, and now we need to integrate the velocity function to get to the position function. So s of t is equal to the integral of our velocity function. So then s of t is equal to, well, term by term integration. This is a number negative 32 times t to the first power. Letter base to number exponent, and my exponent's not negative 1. We'll add 1 to the exponent, divide by that. So I have t to the 1 plus 1 is 2 power, and negative 32 divided by 2 is a negative 16. And then plus the integral of a constant term with respect to the variable t is that constant 60 times t, and then plus c sub 2. Now I'm going to use the initial information from the position setup to find out my constant term for this stage. So again, I'm putting 0 in for the t's, and the output of the position is 6. So 6 goes on the left side and 0 goes in for the t's. So 6 is equal to negative 16 times 0 squared plus 60 times 0 plus c sub 2. And 0 squared 0 times negative 16 is 0 plus 60 times 0 is 0. So c sub 2 is equal to 6. And then my position function then, s of t, is equal to negative 16t squared plus 60t and then plus 6. So that gives you your position function when you were given the acceleration function and some initial conditions.